All right, hello everybody. This video is going through the textbook practice questions for the IB Chemistry SL Reactivity 3.1. The first question says, which is a conjugate Bronsted-Lowry acid-base pair? So when something is asking for a conjugate acid-base pair, it's either asking for the acid and its conjugate base or the base and its conjugate acid. Now, the easiest way to identify this pair is it only differs by one proton. Looking at these answer choices, it's clear that the only pair that differs by one proton, or an H+, is going to be C. Now, looking into this reaction a little bit more, I want to make sure we can easily identify Bronsted-Lowry acids and Bronsted-Lowry bases in an equation like this one. Now remember, when we're talking about Bronsted-Lowry, an acid is a proton donor and a base is a proton acceptor. So if we look at ethanoic acid, which is the CH3COOH, when we look at it on the product side, it loses the last hydrogen in the formula. So it is going to be a proton donor. So this here is your acid, and this here is your conjugate base. Remember, the acid becomes the conjugate base and the base becomes the conjugate acid. Now, by default, you should know that water in this case is the base because ethanoic acid is the acid. However, if you wanted to look at it a little further, water becomes hydronium, and it becomes hydronium by adding one more proton to its formula. And because of that, it is a proton acceptor, meaning that water is the base and hydronium would be your conjugate acid. So if you had a free response question in paper 2 that said to write out a conjugate acid-base pair for this reaction, you have two choices. One would be C in this question, H2O and H3O+, or you could write ethanoic acid and then its conjugate base. Number 2 says all of the following would be described as typical of an acid except. So before we answer this question, I quickly want to go over the properties of acids and bases. So the first one is taste. Acids tend to taste sour, while bases tend to taste bitter. Then we have our pH. Remember, pH of acids is going to be less than 7. And then bases are going to be greater than 7. When we're looking at litmus tests for acids, litmus test is going to turn red. So it's going to go from blue to red. And then for bases, it's going to turn blue. So if you have red litmus paper, it's going to turn it blue. Then for reactivity, with acids, they're going to react with metals to produce hydrogen gas. Then with neutralization, they both will neutralize each other. So essentially acids are going to react with bases to form salt and water, and then bases will react with acids to form salt and water. And then they both will conduct electricity in water because they can dissociate. So again, this question was asking what could be described as a characteristic that an acid would not have. So A says produces bubbles when reacts with calcium carbonate. Now let's just pick a very common acid like HCl. If HCl would react with calcium carbonate, which is CaCO3, it's going to produce the salt, which is going to be calcium chloride. Remember, you need 2 chlorines because calcium has a positive 2 charge. Then it's going to create water. And then real quick, just pause the video and try to figure out what the last product is. The last product is going to be carbon dioxide. Now, carbon dioxide is a gas, correct? That is what the bubbles are. So A would be a typical characteristic of an acid, so that is correct. So we're going to move on. B conducts electricity. Both acids and bases are going to conduct electricity because when they are dissolved in water, they are going to dissociate, meaning that their cation and their anion are going to separate and float around in solution. So because those ions are free floating, that means it can conduct electricity. C says releases heat when it reacts with sodium hydroxide. So again, let's use HCl. If we have HCl and sodium hydroxide reacting in a neutralization equation, that means we're going to form NaCl, which is a common salt, and water. Now, the covalent bonds in water release a lot of energy when they are formed, which is why this neutralization equation is an exothermic reaction. So whenever you neutralize an acid and a base, if we've done it in a lab many times, if you felt that Erlenmeyer or whatever glassware we used, it would be hot. That means that that neutralization equation or reaction is exothermic. So that brings us to D. D says has a soapy feel. A soapy feel is going to be a property or characteristic of a base. So that would be the answer to number 2. Number 3, what is the conjugate base of HSO3 minus? So remember, if we're looking for a conjugate base, that means HSO3 minus is an acid because the acid turns into the conjugate base. And remember, the Bronsted-Lowry definition of an acid is going to be a proton donor. So if we have HSO3 minus and it is a proton donor, then it's going to become SO3 2 minus. So your answer for 3 would be B. 4 says, which of the following can be described as amphiprotic? Remember, an amphiprotic substance can act as both a proton donor, which is an acid, and a proton acceptor, which is a base, depending on the environment that it's in. So due to the Bronsted-Lowry definition, remember, an acid donates a proton, so you have to have hydrogen in your equation, and a base accepts a proton. So when we're looking at number 4, you should be able to automatically cancel out C and D because there's no hydrogen. Now looking at our 2 options, hydroxide and ammonium, hydroxide could technically donate that hydrogen and become an oxide ion. And of course, the most common would be hydroxide accepting a hydrogen and becoming water. So because hydroxide can both donate and accept a proton, A would be your choice for amphiprotic substance. Number 5 says, when equal concentrations of a strong acid and a weak acid are compared, which of the following measurements will be the same? So for the sake of understanding, let's look at a strong acid and a weak acid. We know a very common strong acid is HCl. Let's say we have a 2 molar HCl. And then we also have a 2 molar weak acid. A common weak acid is ethanoic acid. So CH3COOH. Both equal concentrations. One is strong, one is weak. Now, it's asking which of the following, 1, 2, and 3, will be the same for both of these acids. The first one says that the volume of base used to neutralize the acid. Now remember, both of these are acids, so both of these are proton donors, which means when they become a conjugate base, they're going to donate one of their protons. So HCl donates an H+, and then it becomes Cl-. Ethanoic acid donates an H+, and becomes its conjugate base. So as you can see, even though one is strong and one is weak, if they are the same concentrations, they will have the same amount of protons to neutralize said base. So, number one, the volume of base used to neutralize the acid is correct. It will be the same no matter if you have a strong acid or a weak acid, as long as the concentrations of those are the same. Number two says the electrical conductivity. Now, we already discussed what happens when you dissolve these acids in water. It's going to separate the proton from the anion. Now remember, the definition of a strong acid is that it completely dissociates or ionizes in water. Meaning, when you have a strong acid, you dissolve it in water, it is going to become your H plus and your Cl minus, in this case, if we're talking about hydrochloric acid. So all of your acid, your HCl, is going to turn into those ions. Now for a weak acid, not all of the weak acid is going to turn into those ions. Not all of them are going to dissociate. So that's going to be very evident when we were talking about our K values. So Ka is the equilibrium constant for an acid, right? For hydrochloric acid, it's 1.3 times 10 to the 6th. For ethanoic acid, the Ka value is 1.8 times 10 to the negative 5th. Now go back a little bit to what that actually means. Remember, a K of greater than 1 means it's very product favored, right? We're making our products. We're making all products. A Ka of less than 1 means that we're going to be on the reactant side. We're not making all products. We actually have more reactants at equilibrium than we do products. So as you can see, our Ka of hydrochloric acid lies heavily on the right side, meaning we're making those products. Whereas our Ka of ethanoic acid is much lower. It lies on the left side, which means at equilibrium, we actually have more of our original CH3COOH, which is ethanoic acid, than we do our ions. So what this means is that in strong acid like hydrochloric acid, it has a lot more ions in solution than a weak acid at the same concentration does. So the electrical conductivity is not going to be the same with a strong and a weak acid. It's actually going to be much higher in a strong acid. And then the third one, the rate of the reaction with calcium carbonate. Now, the same understanding of dissociated ions or ionized ions goes with rate of reaction, right? So in order for an acid to neutralize with a base, which is what calcium carbonate is, it's a base. In order for it to neutralize, the acid has to donate its proton, which is the H+, and then that will react with the base to neutralize it. So here we have calcium carbonate. So go back to these two equations I did. Remember, with the hydrochloric acid, we are on the right side at equilibrium, meaning we have a lot more H+ than we do at equilibrium for ethanoic acid, because remember, at ethanoic acid, it's lying on the left side. So because we have a lot more hydrogen ions in solution for our strong acid, that means we have more to react with a base, meaning the rate of reaction is going to be much higher with our strong acid than it would with our weak acid. So 3 is also incorrect. So the answer to this question was A. 6 says CH3OH is a very weak Bronsted-Lowry acid. What is true of the ion CH3O minus? So as we talked on previous slides, we know that two species differing by one proton is a conjugate acid-base pair. So because it already stated CH3OH as an acid, we know CH3O minus is its conjugate base. Now, if you didn't already know this, when you have a weak acid, that means you're going to have a very strong conjugate base. And if you have a strong acid, that means you're going to have a weak conjugate base. Now, the reason for that is a weak acid does not completely ionize in solution, which we talked about in the previous slide. And because it only partially dissociates, it means that the acid has a low tendency to donate protons. And when you were talking about the definition of a strong conjugate base, the definition is that it has a high affinity for H+. So the conjugate base of a weak acid, like CH3OH, is going to have a strong tendency to accept H+ ions and reform the weak acid. And again, that's just because the original weak acid did not easily give up H+ in the first place, meaning its conjugate base strongly pulls those back. So with that reasoning, we can identify the answer as C. If you want to go through why the other ones are wrong, we can do that real quick. A, it says, is a good proton donor. Remember, a proton donor is an acid. We're talking about CH3O-, which is the conjugate base. It's not a base. We're not talking about the acid anymore. So in order for A to be correct, it would have to say good proton acceptor. So that's not the right answer. B, it will be present in high concentration in CH3OH at equilibrium. So again, from the last slide, we were talking about weak acids having a very low K value, right? Equilibrium constant. So because they have a very low K value, that means they are on the reactant side at equilibrium. Because they're on the reactant side at equilibrium, that means you're going to have a lot more of your weak acid in solution than you would your conjugate base. And then D, it is a stronger Bronsted-Lowry acid than CH3OH. That is not true. They're a conjugate acid-base pair. Since CH3OH is your acid, then CH3O- would be your base. Number 7 says 2 acids, X and Y, both of concentration 0.2 molar, have pH values of 2 and 4 respectively. Which of the following statements is true? So we have an acid labeled X and an acid labeled Y. They have the exact same concentrations. And the X acid has a pH of 2 and the Y acid has a pH of 4. Now, they are the exact same concentration, which means they have the same moles of acid per unit volume. So, B cannot be correct because it's saying Y is more dilute. Well, it can be more dilute if it's the same concentration. C says X contains more undissociated molecules than Y. Well, X has a lower pH, which means X is a stronger acid, right? So if you have a stronger acid, that means it's going to have a higher dissociation. So it says X contains more undissociated molecules than Y. That is a false statement. It would actually be the other way around. The true statement would be Y contains more undissociated molecules than X. And then D says Y contains a higher concentration of H+ ions than X. Again, that is incorrect because in this case, Y is the weaker acid. And a weaker acid is going to have less H+ ions than the stronger acid because the equilibrium is going to lie on the left side, which is away from the ions. So your answer for this question would be A. X is a stronger acid than Y, and you can get that from the pH. All right, so before we begin this question, just remember your acid is your proton donor, and your base is your proton acceptor. So 8 says, which of the following statements is the defining property of a Bronsted-Lowry base? Well, we know a Bronsted-Lowry base is going to accept H+ ions, so the answer would be D. For number 9, we're looking at the following equilibrium equation. The 2 Bronsted-Lowry acids are, and it asks you to select which ones are the 2 acids. Now looking at the 2 acid-base pairs, remember the acid-base pairs differ by 1 proton. So we have this as one acid-base pair, and then we have this as the other acid-base pair. So When trying to decipher which is the acid, which is the base, remember, acid's going to donate a proton. So since in our blue circles here, CH3OH becomes CH3O minus, it donated that proton. So this is our acid, this is our conjugate base. Then by default, you can assume that NH2 minus is your base, but you could also derive that because it's going to go from 2 hydrogens to 3 hydrogens. So it accepted an H plus ion. So this would be our conjugate acid. So when it's asking for the 2 acids in the equation, we have NH3 and we have CH3OH. Which of the following are conjugate acid-base pairs? Remember, conjugate acid-base pairs are only going to differ by 1 proton. So looking at the first option, HNO3 and NO3 minus, that only differs by 1 hydrogen, so that is correct. Water and hydroxide also only differ by 1 hydrogen, so that's also correct. Now 3 is kind of deceiving because it obviously says 2 H's and you can see 1 H. So I get why you would think, looking at it right away, that it could be a conjugate acid-base pair. However, 2 H plus ions does not equal H2 because you're missing 2 of the electrons, which essentially would be a redox reaction. So because of that, 3 is not a conjugate acid-base pair. And I'm just going to write out the equation just so you kind of understand what I'm saying. So comparing 2 and 3, with water becoming hydroxide, the only difference between the two is that 1 proton. But in order for hydrogen to become H+, it actually becomes 2 H+ ions, and then you have your 2 electrons left over. So this would not be a conjugate acid-base pair because it doesn't differ by 1 proton. It's actually a redox reaction. Which of these reduces the production of acid rain? Number 1 says removing SO2 from power station emissions. So SO2 in the air is going to help in the production of acid rain. So removing SO2 from the emissions that are found in power stations, that would reduce the production of acid rain. So 1 is correct. So you can go ahead and cancel out C as an option. Number 2 says neutralizing acidified lakes with lime. So that's not going to reduce the production of acid rain because it's a local solution to the problem of acidification rather than addressing the source of the acid rain itself. So that's not actually going to reduce the production of acid rain. And then 3, switching to renewable energy sources. That's definitely going to reduce the production of acid rain because renewable energy produces little to no sulfur dioxide, which is going to reduce production of acid rain. So 3 is also correct. So your answer would be B. All right, the pH scale can be used to distinguish between different acids and bases in the laboratory. You are provided with 5 unlabeled bottles which are known to contain 0.1 molar solutions of each of the following. Describe 2 ways in which you could measure the pH of the solutions. So I think the most obvious way would be using a pH meter. And I know we've worked a lot with titrations recently, so another great way is going to be using a suitable indicator. And that indicator will change color when the pH changes, so that is going to be a great way to measure the pH of a solution. Now the next part says suggest expected pH values for each solution. Now this is where memorizing those strong acids and strong bases comes into consideration, because if you know if it's a strong acid, then okay, we know it's going to be between 1 and 2 of a pH. If it's not a strong acid, then we can assume that it's a weak acid. Same with bases. If we know it's a strong base, and we know it's going to be somewhere around 13. But if we know it's a weak base, then we can kind of assume it's going to be somewhere between 9 and 11. So using that information is going to help you with questions like this. So HCOOH, clearly going to donate one of those hydrogens, so that would be an acid. It's not one of our strong acids, so we know it's a weak acid. A weak acid is going to be somewhere in this range. Now, this specific textbook said that it had a pH of 5. I looked into it. I probably would have put it at a 4 to a 6 range, and IB would also do that. So in the textbook, the answer is 5. If you did 4 to a 6, I think you would still get it correct. And then for KCl, KCl is a neutral salt. So that's just a salt. It's an ionic salt. That's not going to have a acidic or basic pH. It's going to be neutral, so that's going to be 7. HNO3 is one of our strong acids that we had you memorize. Strong acids. Because it's a strong acid, I would assume you'd give it a 1 or a 2. The textbook says 1. For NaOH, we know that is a strong base, one of our strong bases we had to memorize. That is going to be a 13. Again, I think if you put a 14, you would still get the points. And then NH3, you should know, is a weak base. That's going to be a weak base and have a pH around 10. So here is the actual mark scheme if you want to pause it and take a look. In the laboratory, some solid sodium hydrogen carbonate was added to an aqueous solution of hydrochloric acid. Formulate an equation for this reaction and predict what you would expect to observe during the reaction. So we have solid sodium hydrogen carbonate, which is the same as sodium bicarbonate, and it's reacting with aqueous hydrochloric acid, and it asks us to predict the products. So I know if I have Na plus and Cl minus in solution, it's going to form NaCl, a salt. And that's going to be soluble in water, so that's going to be aqueous, it's not going to be solid. And then we're going to form water because that NaCl is going to be floating around in water. So we're going to have H2O, that's going to be a liquid. And then finally, if we look at what's left here, we're going to have carbon dioxide, and that's going to be in the form of gas. So when this reaction happens, there's going to be gas bubbles. So we're going to have some gas bubbles. You could also call it effervescence. And then you're also going to have that solid being used up. So your solid will be used up because you can see when you form all your products, there's no solid left. You're just going to have salt dissolved in water and then your carbon dioxide gassing off. And then because we have water formation here, which releases a lot of energy, you're going to have an exothermic reaction. The second part says the hydrogen carbonate can be described as amphiprotic. Explain this statement with reference to the Bronsted-Lowry theory of acids and bases. So amphiprotic, remember, means that it can behave as an acid or a base, meaning it can either give protons or accept protons. So if we're looking at hydrogen carbonate, that's HCO3 minus. So this can act in two different ways. It can act as an acid and donate that H plus to become CO3 2 minus. It can also act as a base by accepting the hydrogen and becoming H2CO3. So it can behave both as a proton donor and a proton acceptor, which means it is amphiprotic. This is the mark scheme given to us by the textbook. Again, not a great mark scheme because it really doesn't tell us any comments or anything to clear up uncertainties. Also, there are a few mistakes. So here it says that Na2CO3 would be made. That's not true because where the heck did the Cl go? So this is the NaCl. And then another thing is a base is a proton acceptor. So this H plus would technically be on the left side of the arrow, which I did in the previous slide, but just to make sure if you're using this mark scheme. All right, and then moving on to the last part of number 12, it says conductivity can be used to distinguish between strong and weak acids of the same concentration. Justify the claim that the use of a conductivity meter is more scientifically acceptable than the use of an indicator. So remember, indicator is color change. So that's a qualitative data point. There's a lot of error in that because someone could see the color, someone couldn't. But if you are using a conductivity meter, you are using a piece of scientific data that is collecting qualitative information that has a much lower amount of error in it. All right, 13. Define the terms acid and base according to the Bronsted-Lowry theory. Distinguish between a weak base and a strong base. State one example of a weak base. So when we are looking at the terms of acid and base according to Bronsted-Lowry theory, I know we've talked about this 100 times in this video already, but remember, acids are going to be proton donors, bases are going to be proton acceptors. Then distinguish between a weak base and a strong base. Remember, a weak base is only going to be partially dissociated or partially ionized, whereas a strong base is going to be completely or 100% dissociated. And then give an example of a weak base. The most common weak base, in my opinion, is ammonia, which is NH3. There's also a few other options that you could do for A. And then B says weak acids in the environment may cause damage. Identify a weak acid in the environment and outline one of its effects. So the options they had in the textbook were sulfurous acid, nitrous acid, and carbonic acid, and then it gave you the reasonings there. Water is an important substance that is abundant on the Earth's surface. State the expression for the ionic product constant of water, which is Kw. So when you are stating the expression for the equilibrium constant of water, it is just Kw equals the concentration of H plus times the concentration of OH minus. Then it says explain why even a very acidic aqueous solution still has some OH ions present in it. So as your concentration of H plus increases, your concentration of OH minus decreases, but there's still some presence in an equilibrium constant. It technically can't go all the way. So there's always going to be some of your products left or some of your reactants left, depending on what side you are on in equilibrium. State and explain the effect of increasing temperature on the value of Kw, given that the ionization of water is an endothermic process. So when you are looking at an equilibrium equation and you have an endothermic reaction, that means your forward reaction is going to be favored. And because the forward reaction is favored, the equilibrium is going to shift to the right. And that's just to use up some of that heat that is supplied to the reaction or the equilibrium. And then D says, state and explain the effect of increasing temperature on the pH of water. Because you have an increase of H plus concentration, your pH is going to go down or decrease. You can also say that the pH was less than 7.